Okay, so here we go. So fundamentals of reaction kinetics. And actually, this is already, these are read by you already on the soft copy of the textbook that I have shared with you. So for a typical chemical process, the very heart of the process, if you notice in the illustration in figure 1.1, is really the chemical steps that brings about the formation of a totally new set of products or a product from the given raw material or raw materials. So the beginning and the end of this particular chemical process are just the physical treatments that, so in the case of the beginning, they make sure that the contaminants or the other things that are together with your raw material will be eliminated. That way it's rendered in a form that it could be reacted with one another. Now, at the end of the chemical treatment steps, you have another series of physical steps now, this time to separate your products. So in particular, in the processing of raw materials, it's very seldom that you only have a single product. So you have several products. So in that case, there's a need for you to separate the main product that you're interested in from the rest, or there's a need for you to purify it from in terms of it being solely separated from the rest. So there should be a set of physical steps that should accomplish that. Now, the physical steps, the beginning and the end of the typical chemical process, the physical steps, these steps are actually the unitary processes or the unit operations. So you have already so far learned 3 unit operations. The last will be learned this semester. And if you notice, there's aren't any chemical reaction that we are considering in all those unitary processes. So we're simply separating components. We're just transferring component from one phase to another. So in the case of the chemical treatment steps, we are really forming new components from a set of raw material. Now this one you can read, so I'd like you to read that on your own. You can read that also from our textbook because that's the exact thing that I have written there. Now, for a simple illustration, the unitary processes, the physical steps before and after the chemical treatment steps are just simply separators. The separators of contaminants or other things that are with your raw material that should not be with it before it's being rendered ready for reaction. And the same thing here with the products that you have formed at the end of the chemical treatment step. So there's a need for them to be separated or purified. Now, the thing probably that brought about the author of our reference book, Chemical Reaction Engineering by Octave Levensfield, probably the thing that brought about him saying that the thing that sets you apart from the other programs in engineering is the subject of chemical reaction engineering. It's primarily because if you could see, when you design a reactor, you don't simply need the reactor design, the knowledge of reactor design to accomplish that. So there's a need for you to have an idea of heat and mass transfer. This probably is the reason, or this is primarily the reason, if I may say, that you have the prerequisite of HMT, heat and mass transfer, for kinetics. So you cannot get kinetics now or chemical reaction engineering unless you have already passed HMT in your language. So you have the need of the knowledge of mass, heat and mass transfer, fluid mechanics, which you of course studied in transport phenomena and even in momentum transfer. Then you need to optimize your process. So there's a need for you to know the economics behind the processes. And of course, the very important thermodynamics, how substances are reacted, the energies related to the substances when they are reacted. Now, kinetics, if I may describe it in just a single word, it just has something to do with rate. How fast will a reaction proceed with the presence of catalysts or inhibitors or without the presence of those two. So all this vast knowledge in engineering, specifically in our field, are related or are rather needed in for us or by us. That way we can design properly a reactor that will produce the desired product or products from a set of reactants. So how do we describe then chemical reaction engineering? So it deals with chemically reactive systems of engineering significance. So I underline really the phrase engineering significance. So they have importance. They're really very important because we cannot bring about the production of new products without this chemical reactive system or reactive systems that facilitate this. Then chemical reaction engineering can also be defined as the discipline that quantifies or correlates the interaction of transport phenomena, one of the unit operation subject, and reaction kinetics. Now, this two is relating the reactor performance, which you will be learning later on, to operating conditions and feed variables. Now, this chemical reaction engineering is that engineering activity concerned with the exploitation of chemical reactions on a commercial scale with the goal of successfully designing and operating chemical reactors. So this is from our textbook, The Exploitation of Chemical Reactions. That way we can produce commercially. So there's this term here, commercial. You are to produce on a commercial scale products. Now, you cannot produce these products without you having to design and operate efficiently chemical reactors. Now, why chemical reaction engineering? So CRE, in short, for chemical reaction engineering, is needed in the development of new and improvement of existing technologies. So there's no way that will be out of the picture, because if it's either developing of new technologies or improvement of the existing ones, we are needed. So in the accomplishment of these two objectives, there's always this search, an ongoing search, a dynamic search for alternative processes to replace old ones. Now, we find other means or routes to make a product from different feedstocks. So how do we make a product from a different set of raw material? That's what you're doing primarily in your research. So in here, we find ways. In CRE, we find ways on how to produce the product from different raw materials. Then this is very, very important. Now, when we speak of economics, there's a need for us to reduce and eliminate unwanted byproducts, because the more unwanted byproducts are present in our set of products after the chemical treatment steps, the more unit operation processes you need to subject this final set of products. So that would entail cost, and that we don't want, of course, to happen. Now, CRE perhaps sets chemical engineering apart as a distinct branch of the engineering profession, according to Octave Levenspiel. Now, what do you expect to learn in CRA? So it's very important that you understand in totality or on a macroscopic view what would be the learnings expected of you at the end of this semester or after the completion of the course. So in CRE, we will develop a general methodology useful in approaching a variety of systems. Now, the system that we will be studying here, although our study will be divided into two major parts, which will be discussed later, will only be limited to chemical systems. The biological and biochemical systems will be discussed in your biochemical engineering later on. So you need to finish first kinetics before you can get your biochem. So our focus is just on the chemical systems. So chemical systems, of course, where engineering reactions are needed. So the core, so the two major parts that I have mentioned in the things that we're going to study for this course in the entire semester will be kinetics, the first half, chemical kinetics, and the second half will be now related to reactor design. So our topics are divided into these two sections. So specifically, chemical reaction engineering has this principal function. So establishing the chemical mechanism of reactions. Now, this is not saying that you are expected already to write down a series of reactions that will bring about a set of products later on, because this one, if you have read your textbook, this was carefully explained by the author that this one entails experience. Even the licensed registered chemical engineers does not have this outright skill of writing the mechanism, the series of reactions that will bring about a particular product or set of products. This entails experience. So usually in this case, you need to know your chemistry together with your chemical reaction engineering. That way, you can correctly write the mechanism of a particular chemical reaction. Now, in here in kinetics, you will discover that the reactions that have been presented to you since Chem 1, Chem 2, in your other professional subjects that entails with chemical reactions are actually the overall reaction only. Or shall we say, it's just the parent reaction that describes a series of reaction that brings about that particular reaction. So you only have one reaction, but actually there's a mechanism why that particular reaction or how that particular reaction was produced. So this is in part here, since this is introduction to chemical reaction engineering only, you'll be able to do this by simply the process of proving. You'll be given a set of mechanism, and then you are to prove that particular mechanism is actually appropriate or correlated to the given rate equation or a given rate law. That you will be taught as well. And there are also examples in Levenspiel on how this is done. But you are not, so I would like to emphasize, you are not to write the mechanism yourself. The mechanisms are given to you. Now, for us to be able to interpret the particular, or to come up rather with the rate law appropriate for a chemical reaction, there's a need for us to collect experimental data. Now, in our case, or in your case, you'll be given already a set of experimental or empirical data. What you do, you interpret this data. That way you can come up with the rate law for the given chemical reaction. The collection of the experimental data will be useless unless we're able to correlate it with the mathematical equation we know as the rate equation. So we should be able to write the rate law, which can easily be written in the form of a rate equation. It's so easy. But this one, the correlation comes after you have already collected the experimental data. The correlation and then the chemical mechanism is also being used in the manner of correlating. Now, designing of suitable reactors is in the end, because this first three actually is just kinetics. The first three here functions. The last one is, of course, has something to do with the design of reactors. But that's not the last, because when we design reactors, we need also to specify the operating condition. Is it adiabatic? Is it constant temperature? Is it constant pressure? Is there a need for us to operate it in a semi-batch process? Those things. The method of control and even the auxiliary equipment. In our case class, the operating conditions that you will only be studying, it has something to do with the operating conditions. As to the auxiliary equipment, we don't tackle that anymore. But in totality, if you are to study really chemical reaction engineering, the auxiliary equipment that goes with your chemical reactor is also being studied. Now, so let's go now as to what concerns chemical kinetics and what concerns reactor design. So when we speak of chemical kinetics, this deals with how fast a reaction proceeds, the rate in which a particular reaction occurs. So this deals with the mechanism of the reaction. And when we speak of the mechanism, it's a set of reactions that brings about the overall reaction which is provided to you. Now, this deals also with the effect of pressure, temperature, composition, and even catalyst on the reaction rate. All of this you will be studying in midterm, because our midterm is all about kinetics and our end term is all about reactor design and has something to do with reactors already. Now, when we speak of reactor design, so there's a need for you, of course, to determine what's the appropriate size for a particular reactor. What will happen if a particular reaction that was facilitated in a given reactor is transferred to a different one? What size of reactor would be needed? Something like that. Now, in terms of configuration, you will also learn whether it would be best to put the plug flow reactor, which you will learn later, after the back mix reactor, or it's the other way around. So you will know what is the best orientation or configuration for your reactor system. Then at the end, wherein in my experience, as to my experience, I always give this to the student to research and report. The consideration of heat and mass transfer already, together with the reactors or with reactor design. Now, it's very important that you understand what's a performance equation. A performance equation simply is an equation which gives you the relationship or gives you a clear picture of the relationship between the output with the things in which, or with the variables that it is dependent on. So the input variables, the kinetics, and the contacting pattern. Now, this is the exact thing that you could also see in your textbook. So when you speak of contacting pattern, this is how materials flow through and contact each other in the reactor. How early or late they mix. Are there some form of aggregation inside or clumpiness? And by very nature, some materials are very clumpy in the case of solids and non-coalescing liquid droplets. So when we speak of non-coalescing liquid droplets, there's no tendency for these droplets to really, shall we say, lump together. So non-coalescing, they never coalesce with one another. Now, kinetics, you know already how fast things happen. If it's very fast, then equilibrium tells what will leave the reactor. Since when it's already equilibrium, there's no transfer anymore, or there's no net formation of the product or products. There's no net formation in the back reaction or reverse reaction for the reactants. It's all happening. Doesn't mean that it already stopped, but nonetheless, there's no net formation of anything. So if not so fast, then the rate of chemical reaction and maybe heat and mass transfer too will determine what will happen. So if we're talking of fast reactions, then that would be equilibrium that will dictate what leaves the reactor. If not so fast, we have to look into the heat and mass transfer operations that's happening in our reactor. Our performance equation is simply this: the output related to the input, the kinetics, and the contacting pattern. Now, this is a table that's presented in your textbook as to how we classify chemical reactions, whether homogeneous, heterogeneous, whether they need the presence of a catalyst or there's no need for a catalyst. So if it's a homogeneous, non-catalytic reaction, then most gas phase reactions are examples of this. One phase non-catalyzed reaction, meaning there's no need for the presence of a catalyst. If it's in the presence of a catalyst, then it's still homogeneous, then that would be most liquid phase reactions. So most liquid phase reactions can have the presence of a catalyst and they are single phase. Now, if it's heterogeneous and does not require any presence of a catalyst, you have these examples here. And if it will require the presence of a catalyst, you also have these examples here. The things that are in the middle, these two examples, or these examples rather, that you have in the middle are intermediate. So meaning somewhere in between non-catalytic, rather in between homogeneous or non-homogeneous, or that's heterogeneous, non-catalytic. So example would be fast reactions such as the burning of a flame. And for the intermediate reaction between homogeneous and heterogeneous reaction, which requires the presence of a catalyst, you have the colloidal systems and the enzymatic and microbial reactions, which you will be studying in detail in biochemical engineering. Okay, so these are just but examples. Now, how do we classify reactions? If we classify them based on mechanism, so the reaction can be irreversible or reversible. You know what a reversible reaction is, and you know what an irreversible reaction is. But I'm sure you also know that in your Chem 1, it was really emphasized that literally all reactions have a certain degree of reversibility. They are only written in the irreversible manner, because one direction in terms of rate is dominating the other. But there is some degree of really reverse reaction for all reactions that is. So they say all reactions are reversible. It's just that the reverse reaction at some point is negligible for some. So it's just written as an irreversible reaction. Now, we can also have simultaneous. So these are the parallel or competing reactions. You will learn that. And the series or consecutive reactions. So this is how we classify it if it's based on mechanism. Now, if we base it on molecularity, meaning the number of molecules of substances that are reacted to produce the product, then we can have a unimolecular reaction, we can have a bimolecular reaction, and a thermomolecular reaction. Unimolecular, you only have one mole. So you simply have the decomposition of one particular single species into another species or several species. Bimolecular, this time you have two moles of each of the species present, and thermomolecular more than two. So that would be thermomolecular. Now, in terms of operating conditions, you can classify reactions as isothermal, isobaric, so constant pressure, isothermal, isochoric, meaning constant temperature, constant volume. It could be adiabatic, it could be non-adiabatic, non-isothermal. The most complex of these are the non-adiabatic, non-isothermal types of reaction, because you really have to consider the effect of temperature, and it really plays a great role in the rate of reaction, specifically, in short, kinetics. Now, you can classify reaction also based on the equipment type and orientation. So you will learn these types of equipments or reactors later on at the end term. So we can have the stirred tank, also known as the back mix reactor or the constantly stirred tank reactor. Then we have the tubular reactor or the plug flow reactor. And we can have this fixed bed, moving bed, and fluidized bed reactors. Now, though simply put, the reactions can be either batch, flow, or semi-batch. This is how they are classified in the end term. It's just either it's a batch reactor, it's a flow reactor, which could come into two forms, and it could be the semi-batch reactor. Now, what are the rates, or what are the things, the variables that affect the reaction rate? You know this in chem, this is fundamental. Homogeneous. So if it's a homogeneous reaction, we have temperature, pressure, and composition. These three affects the rate of reaction. If it's heterogeneous, then you don't, of course, forget these three, and you add heat and mass transfer, because it's rate controlling in the case of very fast reaction. Now, the very important reaction rate, because there's so many ways of expressing rates of reaction. Now, students in kinetics sometimes have some, not all, and there's just a few of them, are confused what is a reaction rate and what's a rate law. So when we speak of a reaction rate or reaction equation specifically, what's the difference between a rate equation and a rate law? When it's said to be a rate equation, the equation is written in the form of a differential equation, just like what you're seeing here. It's a differential equation because you have the presence of the derivatives. Okay, so with the presence of the derivatives, what you have is the rate equation. If we take out this derivatives in the picture, we take it out of the picture, and we just simply represent the rate as what you have probably learned in your phychem as K times the function of concentration. That's rate law. Whenever you don't see any derivative, that's a rate law. But when you see a derivative, that would be a rate equation. Now, the rate equation that you are seeing here tells you that you have related the moles of I being formed to volume of fluid in the reaction vessel with time. So this N is moles of I formed, volume of the fluid is V, and of course the dt is the time. So all these actually rates are dependent on, in terms of their units, are dependent on what is written here on the right side where you have the presence of the derivative. So since this is moles and this is time and this is volume, so in terms of this rate equation, you have its unit in terms of moles of I per unit volume per unit time. Now, we can base it also on the unit mass of solid, but this is only in the case of fluid-solid systems, systems that have solids. So you still have the rate of change of the number of moles of I per unit time here, just like what you have here. But this time, instead of dividing by the volume of the system, you now have divided it with the mass of the solid present in your fluid-solid system. This is still one way of expressing reaction rate when we have fluid-solid systems. Now, when we want it based on interfacial surface in two fluid systems, so like liquid-liquid or gas-liquid, or based on unit surface of solid and gas-solid system, so you have a gas, of course, and a solid, then you express it, the rate of change of the number of moles of I with respect to time should be expressed in terms of the exposed surface, and that's the surface area of your solid. In the case of two fluid systems, this surface will be the interfacial surface. In the case of the gas-solid system, that would be the exposed surface area of your solid. So now, if you notice, all these three in this particular slide only has a difference in terms of the divisor. This one is V, this one is W, the mass of the solid, and this one is in terms of the surface area. I'm not sure if these ways of expressing reaction rate is still written on the third edition, but this can be found in the second edition of Levenspiel together with a particular sample problem. Now, we can also express it in terms of the volume of the solid in gas-solid systems. So if you have a gas-solid system, this could be surface area of the solid, and this is another alternative. And you could also express it in terms of the volume of the solid in your system. Now, it could also be expressed in terms of the volume of the reactor if the reactor volume is different than the volume of the fluid inside the reactor. Now, you may wonder why. How could it be that the volume of the reactor is different than the volume of the fluid inside the reactor? This is in cases wherein you have solids inside your reactor, wherein your fluid, the fluid where the chemical reaction happens is only shall I say, occupying the void spaces in between the solids. So it follows that the volume of the reaction mixture or the fluid inside the reactor is not the volume of the reactor itself. So in that case, if the problem requires you to express the rate in terms of the volume of the reactor, then it should be V sub R. That's in the case of reactors with solids inside, wherein the reaction mixture are only occupying the void spaces in between these solids. Now, you may wonder why, or you may ask, how are we to know which of these rate equation that you have presented will be appropriate for the problem that we are solving? The problem will tell you so. It is the problem that will dictate that you express the rate in terms of this, that you express the rate in terms of that. So it is the problem that dictates what particular rate equation will you need to write. In all these three, if all these rates, if you notice Ri, Ri prime, Ri double prime, and so on and so forth, if they are multiplied to the basis in which they are expressed, that is the rate. So this one is based on volume of fluid, mass of solid, surface of solid, volume of solid, and volume of reactor. They will be all equal. Why? Why would they be all equal? Anyone?